skimpy attendance today.
And a half-lit room. Yeah.
Okay.
Cheese balls, if you care for cheese balls.
The leftovers from Jen
I
visits.
get bouts of them for about 20 minutes at a time.
What'd you guys do?
And I have them
Bernoulli's equation?
since 2:40.
We suspend a cheese ball on the end of a straw. You know, blow through a straw, and the cheese ball floats in the air. You ever seen this?
Pressure.
Not pressure, but, well, I mean, it's pressure, but
Huh.
it's that Bernoulli's equation. Velocity goes up, pressure goes down. Right, you don't have that new fish, right?
No.
What's the strength material of these cheese puffs?
So you are welcome to a cheese puff, if you'd like to have a
See
cheese
how
puff.
much pressure you can apply to your teeth before you crunch.
They are not
I'm gonna
that
test
bad.
them. I'm gonna test them out.
No, they're not that bad. I had like 5 of them.
Okay.
They're a little stale.
Ah, that's why I share them
They
with
could
class.
be worse.
Ah,
They could be way worse.
I'm
I have
really
worse
ready to
off-brand
go.
things.
Alright.
My mom's a big fan of the off-brand.
Okay.
Garbage in, garbage out, like
We're gonna try it.
Wednesday.
What? You like those odd-ones?
That's true. It's so true. Everyone knows the show is really the shows on TV. Your mom did? Yeah.
Okay.
That's why you weren't allowed to watch Rugrats?
I'm not sure how far we're gonna get through the material today, so we may not get to problems until Friday. But, be that as it may, the topic is now plane strain. So we talked about plane stress last time.
Plane trains and automobiles.
Plane strain,
Great movie.
I hate that
Not.
movie.
plane stress. Necessarily. And they may be coincident, but they're not necessarily coincident. In other words, just because I have plane stress doesn't mean I have plane strain and vice versa. So what defined plane stress? If I have sigma x, sigma y, sigma z, tau xy, tau xz, tau yz, what was defined? How did I define plane stress in those terms? That's funny. All right,
By FOSO.
by FOSO, apparently loved by FOSO.
Who's supposed to?
You guys don't know what FOSO is?
Garrick. It's fourth floor Garrick, because it used to be South Hall, because it didn't, before it was named after Garrick, it was South. So 4 South, FOSO. So apparently nobody knows that, but people who live on fourth floor Garrick, but yeah, it's
I've never
nonetheless.
been to Garrick
And
before.
people who are friends.
That's
Imagine-
All right. Plane stress, what defines plane stress?
Yeah.
What defines plane stress?
The planes and stress.
We have sigma x, sigma y, sigma z,
Tau is what?
tau xy, tau yz, tau xz.
Are you looking for the equations?
No, I'm just looking for what defines plane stress. How do I know that I have a condition of plane stress? If I have those 6 variables, what about them tells me, ooh, it's plane stress? So I have sigma x, sigma y, sigma z, tau xy, tau yz, tau xz. Yes?
Quick question, just as a reminder, in like the tau x, y, the x is the plane it's in and y is the direction. it points
X is the
in.
plane that it acts on,
Okay,
the plane normal to the x-axis,
okay.
and y is the direction in which it's. So, how do I know? If I have those 6 variables, how do I know, that's a case of plane stress? Right. Those three being 0 is what defines my plane stress condition. Right? Sigma z, tau yz, tau xy equals 0. And in that case, if tau xy and tau y, if tau yz and tau xz equals 0, then I know, therefore, let's see here, I have epsilon x, epsilon sub y, epsilon sub z, gamma xy, gamma yz, and gamma xz. What are all those? What are those? What kind of quantity are those?
Strains.
Strains. Those are all my strains. So if this is 0, then I know that's 0. If that's 0, I know that's 0. Did you have a question?
Yes. And then the strain Z is going to be 0 too.
Turns out no, not necessarily. Because of what? What characteristic of materials prevents us from being able to say that strain in the Z direction is 0? Poisson's ratio. Right? Poisson's ratio is minus EZ over EX if I'm pulling in the X direction. Right? So that means if there's a strain in the X, then I have a strain in the Z. Right? Potentially. Unless Poisson's ratio is 0, which is not a real material. Yeah.
Okay, so plane stress is only when when all the Z components are 0, but can we still use more circles when we don't have plane stress, when we have full 3-dimensional stress?
So we have not discussed how to do more, how to apply more circles concept. It would actually be more spheres in 3 dimensions.
Okay.
We've only talked about 2 dimensions.
I just thought, like what we talked about yesterday, we can split it up into components and then do.
But it's still plane stress. That was still plane stress. It's
Okay.
just that we had a 3-dimensional material, so we acknowledged that there could be strain in the Z direction.
Okay.
We acknowledged there was a 3rd dimension, but there just wasn't any stress in that dimension.
Right. But there couldn't have been.
But there couldn't have been in the context of the way we do more circles, no. Okay. Okay, so now we have plane strain. I just realized I wrote it incorrectly in my notes. I wrote it as plane, P-L-A-I-N. Okay, plane strain. So now what do you think plane strain means? If this is what plane stress meant, then what do you think plane strain means? Okay, we have the same terms. Let me put them: sigma x, sigma y, sigma z, tau xy, tau yz, tau xz, and similarly epsilon sub x, epsilon y, epsilon z, gamma xy, gamma, what did I do first? yz, gamma xz. Okay. What do you think plane strain means? Somebody venture a guess. Channel your inner kindergartner and be wrong. Be bold. Be wrong. Or be right. But be willing to be either. What do you think plane strain means?
You can have any of
in
them.
the plane.
The strain in Spain stays mainly on the plane. Now, what do you think plane strain means about these values? Look what we did up here, right? We said these were 0 for plane stress. What do you think plane strain means?
The opposite.
The opposite. What's the opposite?
Instead of EX, Y, you'd have the Z strain. Like, I don't know.
Wouldn't it just be not quite the opposite, but like instead of Z, it would be either X or Y? Would be 0?
Nope. But thank you for trying. You each get bonus points for trying.
I'm gonna say it's just gonna be strain in the plane, so it's gonna be like sigma xy,
Strain.
tau xy.
What are 0?
Sigma z and tau yz and xz.
No. that would be plane stress, that's what we started with. If sigma z, this is plane strain.
So is sigma x and y gonna be 0?
No, that's what she said.
Wait, isn't it this,
None of them are
isn't it the
zero.
same thing because,
Huh?
It's the same thing as we had up here for plane stress, but now strain. So the x and y and the xy pieces of strain are non-zero. And the z components of strain are 0. Right, does that make sense?
yeah.
Okay, I'm trying to give you a chance. Okay, and then similarly, these two will be 0 because the two below them are 0. But sigma z is not equal to 0 necessarily for kind of the same Poisson ratio. Although the equation is inverted, but still the same Poisson ratio constraints. Okay. Whew, that was supposed to be the fast part of the lecture. So, remember what we did with plane stress. What did we do with plane stress? So we got sigma x, sigma y, and tau xy. What did we do with that? Yeah, well, okay, with more circles as a
Rotated
tool. Yeah, we rotated it to find what?
Maximum stress.
Right, the principal stresses, the normal, the maximum and normal stress, and the maximum shear stress. So now we're going to do the same thing with strain. We're going to have to figure out how to rotate it, how to rotate strain, and then using that we can find the maximum minimum normal strains, or the principal strains, and the maximum shear strain. Right, so we do the same thing we did with stress. So, what'd you say? What'd you say?
I said what gets z is just coloring in the Moore circle.
Z is just coloring in the Moore circle.
No, I said what finding the strain is just as easy as
Coloring in the Moore circle?
But it's not.
Okay.
I was just wishing.
So, we have a chunk of material.
Is that its technical name?
What's that?
Is that the technical name?
Yeah, this is a chunk. One regulation chunk. And we're going to take it from the xy coordinate system to the x prime, y prime coordinate system. So we're going to rotate it by theta. We want to find out what happens to our strains. So first, let's take our thing as dx and dy big. That's the size of our box. And it has a diagonal ds. Actually, we go to a different color here. And then I'm going to strain it in the x direction. Apply a strain in the x direction, so that my ds now has changed. Do we see that?
So you're stretching it and then.
So this distance here then is going to be epsilon sub x times dx. And I'm stretching it in that direction. Good? And I want to find out how much is my S elongated. Right, there's a couple different things that happened. S is getting, my ds has gotten longer, but it's also changed its angle. Right? It has a little alpha in here called alpha 1. Right, so I've rotated ds and I've made it longer. So I want to find out what is my change in ds. Or in other words, I'll call this dx prime. What's that distance, dx prime? So dx prime is just going to equal epsilon sub x dx times the cosine of theta, right? Because this is a right triangle in here, and that angle's theta. Everybody see that?
Wait, what are you calling your DX prime up there?
Just that little length. This little piece.
Okay.
The elongation in S.
Hey, how are you saying minutes times cosine theta?
This angle's theta, so this angle's theta, and that's a right triangle right there. So I'm taking epsilon sub x dx times the cosine of theta to get just that long leg of that triangle.
Okay.
Follow me?
Mhm.
Okay. Similarly, alpha 1 times ds, right, it's angle times the length, is equal to epsilon sub x dx sine of theta. That's the short leg. The angle times the radius gives me the distance out there. Everybody see that? Okay. Or I just rewrite that as alpha 1 therefore is equal to epsilon sub x times dx over ds sine theta. Follow that process. So I've found the elongation and the change in angle due to those two pieces. Due to the caused by epsilon sub x. Blake, you want to ask a question?
Well, I guess I'm having a hard time believing that the new ds is equal to ds plus dx prime.
It's not
Oh,
entirely.
okay.
It's not entirely that.
Okay.
Okay, because the new ds has a different length
Yeah.
and a different angle.
Yes,
So
okay.
there are two pieces involved. Okay.
Okay.
And as you can see, by virtue of the fact we're using dx here, we're going to do this in the limit, right? As dx gets to be 0, so that these two will actually be equal to each other. The change in length will be, it's okay.
Okay.
I'm saying it all comes down to the ultimate limit,
Okay.
right? Because alpha is small, and so we're making an approximation here that as we drive dx to 0, that approximation goes away, and we end up with that. Okay. So I just want to make sure you understand why an epsilon, how an epsilon x in this direction doesn't just automatically correspond to a dx in that direction. There's a relationship between the two. Right, there's a cosine theta relationship. Okay, and that an epsilon x also causes this rotation. So if I stretch it in this direction, I'm not only stretching it along its diagonal, but I'm also rotating its diagonal. Once you see that both pieces are involved. And I can do the same thing, taking the same square. And now if I stretch it in the y direction, now I have what I'll call alpha 2, right, because now I've rotated it up the other direction. And similarly, here would be epsilon y dy. And then there would be a component of that dx prime due to that. So if I elongate it that way, I'm also going to get a dx prime. And I'm going to get an elongation of my diagonal due to a stretch in the y direction. Yeah.
Sorry, going back to the first one real quick, if you know you just have a strain in the x direction, couldn't you just like find a new, instead of drawing a triangle like above that little strain sliver, I guess, like finding the triangle above, couldn't you just use the trig of the new, like your dx plus strain times dx and then your dy? Like, couldn't you just figure out the lengths and the angle that way?
So you could, but you're going to have a much more complicated expression.
Okay, but it's.
Because if you think about this is not really a right triangle in here. Right, I don't have a nice, I guess this one's a right triangle. So I can do this, right?
Yeah.
So this thing I would still need to know this piece, because this thing is gonna be related to the full length here and the sine of alpha, or the cosine of alpha, rather.
Okay.
Right, so I'm gonna end up with ds plus dx prime is equal to the new ds times the cosine of alpha. But alpha itself is then gonna be expressed in terms of this, and it becomes much more complicated. Okay, there are other ways of doing it, but it's a more complicated solution.
Okay.
Okay, so here we're just, by solving for this dx prime, we can bring the dx prime into every single one of our equations, because this is the one we care about. How much is it strained in the x prime direction?
Got it.
Okay, we just want to know what's the elongation in the x prime direction. So let's solve for that, and then come back and add it in at the end. And actually, we'll divide it out at the end. We'll divide dx out at the end. Anyway, so in this configuration, again, since this is theta here, it turns out if you do the geometry, you find that that's theta up there, this angle length this time. Okay. So now, dx prime is equal to epsilon sub y dy times the sine of theta. Because now the dx prime is the opposite leg for that triangle. And if you do the same kind of approach with alpha 2 is going to equal epsilon sub y times dy over ds cosine theta. Because now it's, this piece is the cosine of the adjacent leg. Everybody follow that? Okay, so we're trying to find how much it rotate, how much it stretch. Third, we can apply plane strain, so we have a third strain. The third strain, though, that exists in plane strain is a shear strain. So now we apply a shear strain, and it looks like this. That's the shear strain, gamma xy. That make sense? Okay. So now I have a new diagonal here that again has a component dx prime on the x prime axis. Recognize that this little stretch here, this is gamma xy dy, that's how long that piece is. And therefore that's how long this piece is. So dx prime is equal to gamma xy dy, and again here's theta in this picture. So it's again cosine theta, and alpha 3 now, the third alpha, is going to use the sine. It's going to be gamma of xy dy over ds times the sine of theta. So those three strains each contribute both to the elongation and to the rotation or shear of the member. You ever see that? So if I want to add the total dx prime is the sum of those three. Ex dx cosine theta, ey dy sine theta, plus gamma xy dy cosine theta. I'll just write it down. Ex dx cosine theta plus ey dy sine theta plus gamma xy dy cosine theta. Right? That's my dx prime, the three pieces. If I want the strain in x prime, that's the elongation, dx prime, divided by ds, the original length, right? Change in length divided by length is my strain. So I divide through there by ds, and I end up with epsilon sub x, dx over ds, cosine theta, plus epsilon sub y, dy over ds, sine theta, plus gamma xy, dy over ds, cosine theta. Almost there. One more step. The next step is to recognize that dx over, what is dx over ds? Go back to my original drawing. What is dx over ds? Look at my original square, my original chunk, I believe. What is dx divided by ds? Cosine theta. See that? So what I end up with then is that epsilon sub x prime is equal to epsilon sub x cosine squared theta dy over ds sine theta plus epsilon sub y sine squared theta plus gamma xy sine theta cosine theta. So that's how I can rotate it. I can find the strain in the x prime direction by using the strains in the xy coordinate system and the theta by which I'm rotating. Okay. Similarly, you would get in the y direction, dy prime, or epsilon sub y prime, is just ex prime, but now adding 90 degrees to theta. Right? I just replace all my thetas with theta plus 90 to get to this axis. Right? See that? So if I replace all my thetas with theta plus 90, then I got epsilon sub x sine squared theta plus epsilon sub y cosine squared theta, in this case minus gamma xy sine theta cosine theta. And then it turns out it's a little more complicated to do the angles. I have to add the angles. So it'd actually take alpha 2 minus alpha 1 and minus alpha 3, because alpha 1 and alpha 3 are negative angles. Alpha 2 is a positive angle. But I also have to do the same for all the angles. There would also be beta angles for the y-axis. Right? So what I'd have to do is I would have to find my alpha, so I would take my total alpha equals minus alpha 1 plus alpha 2 minus alpha 3, using these things. Replacing again, dx over ds is cosine theta, dy over ds is sine theta. Right? But then I would also do that, I would have to add beta, which is going to be, there's going to be a beta 1, a beta 2, and a beta 3. For the y-axis. Anyway, what you end up with then is the total gamma x prime y prime. Okay, for the alpha plus beta. It's minus 2 epsilon sub x minus epsilon sub y sine theta cosine theta minus gamma sub xy sine squared theta minus cosine squared theta. Okay, but that's kind of, okay, so, I mean, we've got it, solved it. Got some weird kind of sine squared, cosine squared things in there. So we're going to use the double angle approximations, the double angle equalities. Remember the double angle equalities that we used last time? In order to get everything in terms of 2 theta p and 2 theta s, you guys remember that for the plane stress? We're gonna do the same thing here. Use the double angle things to get rid of these cosine squared, sine squared things. And when you get, actually I'm one too far, hold on. When you get epsilons of x prime or y prime is they're going to equal epsilons of x plus epsilons of y over 2 plus or minus epsilons of x minus epsilons of y over 2 times the cosine of 2 theta plus or minus gamma xy over 2 times the sine of 2 theta. And you get gamma x prime y prime over 2 is equal to minus epsilons of x minus epsilons of y over 2 times the sine of 2 theta plus gamma xy over 2 cosine 2 theta. All right. That look familiar? Where's it look familiar from?
And that basically are all equations for stress, but with sigma, epsilons instead of sigma.
Right, it's the same relationship as we had for plane stress. Okay. So, work through it a piece at a time, but in the end, we end up with the exact same relationships. Where now, what was sigma x has now become epsilons of x, or was sigma y has become epsilons of y, and what was tau xy has now become, and this is the only really tricky part of it, gamma xy divided by 2. You have an extra 1/2 factor in there. But otherwise, the equations are the same things we had before.
So we can still use the circle.
So we can still use the circle, right? Bottom line is, we still get to use more circles for this. The functional behavior is the same.
That's totally right. Turns out I was right. Just color them in. Call them stress circles.
Yeah, I'm not sure how coloring in equates to calling them strange, but so just like we had before, we'll have principal strains. All right, the principal strain. So that's how we rotate to a particular angle. But we'll do the same. Take the derivative, set it equal to 0 to solve for theta, kind of thing. And we get principal strains that are the same. Ex plus Ey over 2 plus or minus the square root of epsilon x minus epsilon y over 2 squared plus gamma xy over 2 squared. Right? Same relationship we had for the principal stresses, except now tau has been replaced by gamma over 2. And the tangent of 2 theta p for the principal strains is much like it was before, minus epsilons of x minus epsilons of y over gamma xy, where the factor of 2 that we have to put into the gamma removes the 1/2 that we had in here in the tangent expression for the stresses. Right, because this was Ex minus Ey over 2 divided by tau, and the stresses, that extra divided by 2 gets canceled out. Okay? And then similarly, the in-plane maximum shear stress is just the radical piece, epsilons of x minus epsilons of y divided by 2 squared plus gamma xy over 2 squared. And the tangent of 2 theta s is equal to gamma xy divided by epsilons of x minus epsilons of y. I got those backwards. Sorry. Okay. So for plane strain conditions, we can also jump on, do our Moore circles. And all that looks just the same as it did for stresses. What's that?
Except we gotta color it in.
So we have a Moore circle. Right, this value here is epsilon x plus epsilon y divided by 2, the average strain. We have some diagonal across there. This value here is epsilon sub x. This value here is epsilon sub y. This is epsilon on that horizontal axis. The vertical axis is gamma over 2. Again, inverted, just like it was before. And this value is gamma xy over 2. That's minus gamma xy over 2. This value here is epsilon 2. This value here is epsilon 1. And this is the in-plane max divided by 2. Yeah.
I have a question. It seems to me like you could use more circles in other applications other than plane strain and stress. Is that, is this like a engineering tool that we use in lots of different things, or is it just used for this?
So it's used, so you can't use it for three-dimensional stress, okay? Because the reason we use it for plane strain and plane stress is because they happen to be, the relationships happen to, sort of work the square, the sum of the squares or whatever, so it looks like a circle. Right? It has the sort of shape of a circle, wherever that. Oh, over here, right here, right? I take the average strain to the other side and it behaves like a circle. So, or you have to square both sides and add them, how you did it, anyway. And so it behaves that way, but it's not necessarily, I'm not familiar with any place else that we use it, other than this application. I mean, it's just a graphical representation of an equation that happens to have x squared plus y squared equals r squared form. Okay. Oh, and I forgot to put r then as the square root of epsilon x minus epsilon y over 2 squared plus gamma xy over 2 squared. And the 3D thing still applies the same as well. So in 3D material, in a plane strain condition, but in a three-dimensional structure, we still have the this kind of rule that applies. In this case, we have a compressive strain and a tensile strain. If we drew the axis down the left-hand edge, it would be 2 tensile strains. Does that make sense for everybody? We can still do everything the same. It's just strains instead of stresses. Any questions before we at least start the first problem? All right, I don't see any hands in the air. So I'll trust that you don't have questions and we can start. Problem 10.4 at the top. So let me erase from here over. All right, so let's look at 10-4. The state of strain at the point on the gear tooth, the little chunk from the center of the gear tooth, has components EX equals 850 times 10 to the minus 6, EY equals 480 times 10 to the minus 6, and gamma XY equals 650 times 10 to the minus 6. Use the strain transformation equations to determine the in-plane principal stress strains and the maximum in-plane shear strain and average normal strain. In each case, specify the orientation of the element and show how the strains deform the element within the XY plane. So what do?
So maybe we can start out drawing a box or a square to represent the tooth.
The chunk of the tooth?
Sure.
Okay, so I draw a little box.
We can put down our epsilon x, our epsilon y, and our gamma xy on the chunk.
How would you do that?
We can't just label them.
So, before we did a free body diagram with a chunk, and we drew stresses on because they're forces.
Right.
How do you draw strains?
We can draw the strains as like displacements, locations or
So,
displacements.
I could do something like, I could do something, say, well, that's my epsilons of y, and that's my epsilons of x. My epsilons of x is bigger than epsilons of y. How would I represent gamma xy?
We can do a dotted outline with of it shifted in a shear direction.
Okay.
Right.
Right, okay, there it is. Now what? What's it asking for? In-plane principal strains. And what does it suggest that we do to get there?
Strain transformation equations.
Use the strain transformation equation to find the in-plane principal strains. So where might I get such an equation? Hmm?
In the book.
Well, we could get in the book.
Or the ones you just stepped out from.
All right, they're the ones on the board, right? These are the in-plane principal strains, right? So in this case, I just have to plug in. Now, it turns out, you'll notice that your book, the section at the beginning of the book that you get, on your exams, does not have expressions for the in-plane principal strains. Okay, it's not, that's absent from the front of your book. Why do you think that is? Because of the same thing as the stress, you just have to know to replace tau xy with gamma xy over 2. Okay, otherwise the concepts are the same. So you're only going to get that equation, you're not going to get the strains. Okay, so you got to be able to recognize that. But I can just plug in numbers. Epsilon 1 and 2 is equal to, what's epsilon sub x? 850 plus 480 divided by 2 times 10 to the minus 6, plus or minus the square root of 850 minus 480 divided by 2 squared, plus gamma xy is 650 divided by 2 squared times 10 to the minus 6. Since 10 to the minus 6 is prevalent throughout, I could just pull it out. And I get epsilon 1 is equal to 1039 times 10 to the minus 6. Epsilon 2 is equal to 291 times 10 to the minus 6. Pretty straightforward. Okay, what's the next thing I'm looking for? And that answers part A, the in-plane principal strains, right there. Means that in some angle, at some angle, whatever it is, I have a principal strain of 1039 in one direction. And so drawing your picture, it's probably going to be somewhere in that kind of a direction. Like that's where I have a significant strain. And then perpendicular to that, I kind of have a lesser strain. Right, so in some set of orientations, I'll give you that.
So now you find maximum in-plane shear strength.
What's the maximum in-plane shear strain?
Square root. Square root of, that's what we have.
This way is the
Plus and minus.
That's this piece, right? So it's just this piece. Right? Okay. And so then I find, where do we have that? B, that is gamma in-plane max is 748 times 10 to the minus 6. Okay, am I done?
What's the angle?
In each case, specify the orientation of the element and show how the strains deform the element within the xy plane. So I've got to specify the orientation, I have to find the angle. So what angle am I looking for?
Oh, does it in both cases?
What's that?
It says it once in each case.
Okay, so I need to know, what am I looking for here? What am I solving for here?
Okay.
Theta p. Right, so how do I get theta p?
Gamma xy over tangent to theta equals gamma xy over sigma x plus
Right,
sigma.
so the inverse tangent of 650 divided by 850 minus 480.
All over two.
What's that?
All over two.
No, 2. Oh, yeah, right, divided by 2, right. Right. Equals 30.18 degrees and 120.18 degrees. Why did I get two numbers?
What's the tangent side of
Because the tangents are weird. Do those two numbers mean something?
Yeah,
When you have two angles.
Right, that's the two principal axes separated by 90 degrees. Right. Okay. So roughly 30 degrees, it's probably reasonable based on sort of the estimated drawing that I did on the board. Right. Okay, and 120 will be over here. Then what else do I need?
Yeah.
Theta S. How do I get theta S?
Equation you just did in front of it.
Yeah, I could do that.
Or you just add 45 degrees.
Or I just add 45 degrees to what I have before. Right. 75.18 degrees. Or alternatively, subtracting 45 would give you the other one, which is 54 minus 14.82 degrees would be the other one. Make sense? It's all good? Yes, sir.
What about the average normal strain?
What is the average normal strain? Somebody tell me.
The average normal strain.
Mm-hmm.
Sigma epsilon,
Right, so it's just this piece. Right. So, I mean, in the process of solving this, I solved for that, which is what, 665? Is that right? 665? 665, I think it's 665. Okay. So the reality is when we get to doing more circles, it makes it a lot easier. We just we have to calculate these pieces individually for more circles. All right, we calculate the center, so we know where to put the center. Then we calculate the radius. And we draw the whole thing, we've got all the other pieces right there. So we'll do some more problems like that next time. When's soccer over?
We're in, second round of the playoffs right now, it's 3 rounds, for our conference tournament.
Right.
And then after that, if we win it, then we'll go to, be like a regional playoff for nationals, national tournament, so it could go as long as late November. So,
It's chilly out there.
not in Miami, Florida, but we make it down there.
Oh, yeah, very nice. So, when's the next round?
Saturday.
Is it here still? We're second seed, so.
Yeah.
So, and did the first seed win their first round as well?
Yeah, they did. That's, I would, they'll probably,
Surprise.
make it to the championship.
Oh, really?
So, yeah.
Is there anybody else good that you can worry about?
Yeah.
So who we play this week then?
This week is Goshen.
Goshen.
The good old Maple Leafs.
The good old what?
Maple Leafs.
The Maple Leafs? The
Maple
Goshen
Leafs.
Maple Leafs?
Goshen Maple Leafs.